Our next ChemX talk speaker is one of our college's own faculty members, Professor Jeff Reimer. Jeff received his bachelor's degree from UC Santa Barbara and his doctorate from Caltech. Prior to his faculty appointment at Berkeley, Jeff was a postdoctoral fellow at IBM Research in Yorktown Heights in New York. And during his time at Berkeley, Jeff has done so many things, I can't possibly recount them here. I'll just name a few. He has served as Associate Dean of the Graduate Division, where his responsibilities included the assessment of all of Berkeley's doctoral programs. He also serves currently as a member of the Board of Trustees for Franklin University, Switzerland, and he has served as the chair of the governing board for the Council for Chemical Research in 2015. Jeff is a pioneer in the engineering science of nuclear magnetic resonance and has been recognized around the world for his contributions in that field. But he has also won several teaching awards, culminating in the UC Berkeley Distinguished Teaching Award, which is the highest award bestowed on faculty for their teaching. And oh yes, last but certainly not least, Jeff is presently in his 12th year as Department Chair of Chemical and Biomolecular Engineering, and yes, that is a record, and we're delighted Jeff is setting it. And he is also the Warren and Katharine Schlinger Distinguished Professor in Chemical Engineering and the C. Judson King Professor of Chemical and Biomolecular Engineering. So Jeff's ChemX talk today is titled Climate Change, the Verdict is In.
Let's start with a movie. Concentration of carbon dioxide in the atmosphere, parts per million. Place on the planet, very famous place on Hawaii Island, South Pole. Here's time, concentration of CO2 in the atmosphere. Here's a clock. Here are stations coming online and offline and contributing to these data. And the question we're asking is our atmosphere changing or not? So as we follow this graph along, you'll notice that the Hawaii measurements go up and down every year in a cycle, and the measurements from the South Pole also go up and down, although they're out of phase with the Hawaii cycle. Some data are noisy. Some data are less noisy. I think the trend is pretty clear to you. It's going up. The movie stops in 2016, and it'll be just about 400 parts per million, and today we are at 413 parts per million. This graph shows this trend quite nicely. Now we're going to continue with the Hawaii data back to 1956. And now we're going to jump and use tree ring and ice core data to go back in time to about the year 0. Here's where we are today. Here's where we have been. Now we're going to use ice cores from Antarctica to go back in time now 1 million years. And you see the concentration of CO2 goes up and down. It fluctuates a lot. We're going to use some different ice cores coming up soon to collect more data. Here's where we are today. All these cycles that go up and down. Notice there are ice ages that are present throughout this time. That's back 1 million years. A lot of very talented people contributed to creating these kind of data. So it's not just from a group, and it's not just from a country, and it's not just from a lab. Many people have worked to make this so. So here's a picture of the concentration from Hawaii. This is due to a very famous scientist named Dave Keeling. He died a few years ago. And this curve is named the Keeling Curve in honor of him. And it's a national landmark for the American Chemical Society. And the question comes up is, why is the CO2 going up? And a hypothesis that's going through your mind, as it does through all of us, is it must be due to combustion. So here's a chemical formula. Here's all the stuff we burn. We burn it in oxygen. And the assumption is that if our engines are responsible for increasing CO2, then we must be consuming oxygen. This is what elementary chemistry tells us. It was Dave Keeling's son, Ralph, who took up that charge, and in the mid-1990s published a series of landmark papers in which he showed the concentration of oxygen in the air is decreasing, and the stoichiometry matches provided you account for the CO2 that goes into the oceans and into the soil. So where is the CO2 coming from? It's coming from combustion. How can that possibly be? The Earth's atmosphere is so big. Well, let's just take coal-fired power plants, for example. In the year 2017, 1,400 million tons of CO2 were emitted into the atmosphere just from coal-fired power plants. What does that mean? Well, let's compare that in the same year to the total amount of plastics produced in the world. And you recognize that by weight, we put 4 times as much carbon waste into the atmosphere as we produce plastics on the planet. That's just from coal-fired power plants. The Earth's atmosphere is changing. It's due to our combustion, and the scale makes sense when you think about our industrial processes. It's due to us, and we've made the air our receptacle for carbon waste. What are some of the consequences? Well, the obvious one would be temperature. Of the many graphs that we could show, I like this one the best. Time will increment here. Here's a place on the planet, and a blue line represents it's cooler than average, and an orange line represents that it's warmer than average. And we can walk through this clock in time, and the data speak for themselves. And as I'm sure you probably know, 4 of the last 5 years have been the hottest in recorded history. You've probably heard, maybe you could have signed an agreement to keep the planet at 2 degrees C. Well, we haven't signed that agreement. We could have. Here's a map of the United States showing the change by place on the United States based upon an average. And you see that there are regions in the United States in which we've already exceeded the 2-degree average. So while the planet as a whole is still only about 1.5 degrees, some places experience more of a temperature rise than others. And this has a lot to do with the presence of ice on the ground before the climate began warming. So what are some other consequences? How about weather? That's something we hear about in the media. Was yesterday's or last week's or last year's hurricane due to climate change? Well, we need to ask the following question. If the average Earth's temperature changes a little, what happens to the probability of events that are very rare? This was a question Jim Henson took up a few years ago in a landmark paper. This paper is a little bit old, but it is one of the most powerful graphical depictions I know of that shows why we have extreme weather. So let's take the average temperature in San Francisco, we'll make an array of those set of numbers, and we'll make a plot of probability as a function of temperature. Not unlike the grading curves in, for example, Professor Arnold's class. We have an average. In San Francisco, the average is 54 degrees Fahrenheit. That's downtown San Francisco. And so these events here, the 3 sigma and 2 sigma events, 3 and twice the standard deviation, ought to be very rare. And so Jim and his colleagues asked the following question. How much of the Earth has experienced a temperature change larger than 2 or 3 sigma? The notion you have a Gaussian, a small change in the average, has a big effect on the tails. What do the data say? So Jim and his colleagues made a map of the planet, and on that map they superimposed whether that particular region had experienced cold 3 sigma events or warm 3 sigma events, 2 sigma and so forth. Here we are. 1955 relative to the average. Some were warmer, some were cooler. 1965, some were warmer, some were cooler. 1975, some were warmer and cooler. You ready? There we go. The last data set was 2011. Demonstrating well that a small change in the average will produce a big effect on the tails. And extreme weather events are much more likely to be occurring because of this. So, how about other things? Sea levels, glaciers, ice levels. We have data for those. Here's a landmark paper from 2015 which made the following unusual suggestion. The level of the global waters as a function of calendar year, a lot of data, a lot of noise. And their argument was, really in the first half of the 20th century, the rate at which the seas were rising was about 1 millimeter per year. Because the planet is warming, the density of water changes, and the seas rise. But interestingly enough, in recent years, it looks like it has accelerated, and we are now 3 millimeters per year. This was a very controversial and disturbing result. An entirely new group came and reanalyzed the data, And what do they get? Another landmark paper that confirms that indeed we have a rate and it is accelerating. Why is it accelerating? Because there's another contributor to global sea level rise besides warming the oceans. And that contributor is melting ice. Here's a map of the sea level contribution just from Antarctica as a function of time. The green, the yellow, and the red are a model. Let's ignore those for a moment. The blue are the data with the error bars. So as we warm the planet, ice melts and the sea levels rise, not just because the water's warming, but because we're filling the bathtub. That effect is not uniformly felt around the planet. Here's a little cartoon from Wikipedia that shows that ocean currents bring, for example, to the southwestern Pacific, warm waters come near the surface. And what are the consequences? The consequences are that sea level rise is not uniformly felt. And so, for example, in this region of the world, sea level is rising faster than in this region of the world. And there is some irony, isn't there, to the fact that the wealthiest nations of the world that contribute the most CO2 in the atmosphere are least affected early on by sea level rise, and the poorest people of the world are most affected by sea level rise. How about glaciers? Let's go to the Rhone Glacier in Switzerland. Here's a picture of the Rhone Glacier. You see the front of the glacier right there. Here's a famous pass that you can drive over. My daughter and I hiked along this trail and took measurements along the front of that particular glacier. That was a picture from 2014. Here's an artist's sketch of that same area in 1850. Notice these buildings in this village in the foreground. Those are those buildings in village here. And you see the glacier was all the way at the village. By 2050, the Rhone Glacier will be gone. And the Rhone River, one of Europe's major contributors, will be a seasonal river and not be running year-round. We have a lot of data on glaciers. Look, this is the number of glaciers that have been measured, either their mass or with their front variation, just like I showed with the Rhone. And the answer is the glaciers are shrinking rapidly. Here's all the glaciers in this curve with the error bar shown by the width of the line. And here are 30 famous glaciers extracted from that data set. So the glaciers are shrinking. How about Arctic ice? So this is in the North Pole. Here's the extent of the ice in the North Pole. It's shortest, it's less in the summertime and highest in late winter. Here's the average from those 2 or 3 decades. Here we are 2018, here we are 2019. The Arctic is expected to be ice-free in the summer within your lifetime. Here's a map of Antarctica. Let's go down to the South Pole. The size of the circle tells me the size of the change in ice. Reddish means that ice has shrunk, and blue means ice has grown. Here's for different portions of the Antarctic Peninsula. Okay, that's this decade. Shall we march through the decades? 79 to 89, 89 to 99, 99 to 2009, and here we are, the last decades. The ice is retreating from Antarctica at ever-increasing rates. So, rising temperatures, extreme weather, all these are attributes that are associated with CO2, which you and I put in the planet's atmosphere as our carbon waste receptacle. Mathematical models can allow us to look both back in time and see what contributions appear in climate change and what didn't. These mathematical models are amongst the most difficult intellectual challenges of your generation. Let's take a look at what they say. This is the data, the planet's temperature, hotter and colder as a function of time, the observed data. And now what we're going to do is parse that data out from the mathematical models according to, for example, how the orbit of the Earth changes around the sun. What's another possible example? The solar output, because the solar output fluctuates. Let's see, there's a third one. Oh yes, volcanoes. And you notice there's a couple of volcanic eruptions in the later part of the 20th century. And we can add them all together. These are the natural forces that would drive climate change, and we can compare that to the data. Now let's look at the forces that are due to us. For example, we change the way we use land. That affects temperature. We introduce ozone into the atmosphere. That affects temperature. We introduce aerosols into the atmosphere, and that decreases the temperature because the aerosols reflect light. And then, of course, we have greenhouse gases, such as methane and CO2, and they have their own contribution. And we can add up now the human contributions and compare them to the data. not a bad fit. But when we take the human factors combined with the natural factors and took at the best analysis, we see the mathematical model matches the data pretty well. That gives us confidence that the physics and chemistry we put in those models is at least at some level correct. And so we can go forward in time. This is the coldest nighttime temperature if we kept the planet to 2 degrees C. We're nowhere near making that goal, but let's suppose we did. This is what the Arctic looks like. At nighttime, it's 8 degrees higher than it is now. And that's because the ice retreats in the Arctic, it absorbs more sunlight, and it heats up more quickly than the rest of the planet. So the atmosphere is changing. The change is due to combustion. The climate is changing. Radiative forcing is the mechanism by which that happens. It turns out if you go back in time and look at the history of the planet Earth, there are incidents in geological time in which there have been spikes in CO2 concentration. And if you look at how the Earth responds and recovers, it's about 200,000 years. So a couple 100,000 years from now, whatever we've done to the atmosphere will sort of be smoothed out and we're all in good shape. So I suspect you're worried, like I am, that maybe there's something we can do in the meantime. There can be a plan, and the College of Chemistry at UC Berkeley is definitely part of that plan. So for example, these are the kinds of things that people envision taking place as public policy and personal choices. So for example, we could design and build our buildings so that they use less energy 24 hours a day. We are using cleaner fuels, but not because we care, our government is not using cleaner fuels because the government cares about climate change. Cleaner fuels are happening because hydraulic fracturing has produced natural gas at such cheap values that it replaces coal, which is a terrible fuel for generating electricity. Hydrogen, wind and solar power, what we're at now, a couple cents a kilowatt hour for wind and solar power. This is a great opportunity. Surprisingly, the joke that I heard early on in my career that if you plant a tree or save the environment, laugh, laugh. It turns out that modern science and contemporary science is arguing, oh yes, it does matter because it's not just the tree. It turns out the rhizosphere, this region between roots and rocks, is very much a dynamic part of the tree growth, and fungi and bacteria and all the things that are happening in soil turns out take up as much or more carbon than the tree itself. And there's a movement now to imagine planting 1 billion trees. 1 billion trees would take up 1/3 of the carbon dioxide that we've put into the atmosphere. That's certainly a possibility. This is dead, right? It's dead because it's expensive. All right, at 25 cents a kilowatt hour, nobody's going to build a nuclear power plant. So this technology has to change dramatically, or we just leave it behind. I want to call your attention to these 2 items here. So can we take carbon dioxide out of the air? And can we attach a device onto a coal-fired power plant such that we remove the CO2 from the exhaust stream? The International Panel for Climate Change says this has to be part of the toolkit to deal with decarbonizing the atmosphere. It's an extremely difficult problem. These exhaust gases from these power plants are toxic. And so handling them at the volumes that we need is incredible. Capturing CO2 directly from the air is a very difficult problem. It's 413 parts per million. That's very challenging. And so what the chemists at Berkeley are doing is they're imagining taking exhaust gases, passing them through technological devices in which the CO2 is removed. The CO2 is then stored underground in the very same places in which we took the oil and natural gas out in the first place. And adsorption is a key technology. That is, you blow the gas over a powder, and the powder selectively absorbs CO2. And that's where we're going, also doing that with direct air capture. So I just closed by saying there's a class of materials in which my colleague, Professor Yagi, is the pioneer in this area. It's a class of materials called metal organic frameworks. And in the past 3 or 4 years, Berkeley chemists have delivered direct air capture with these materials. They've delivered capture from coal-fired power plants, and they've delivered capture from natural gas-fired power plants. And on the horizon is the ability to capture CO2 from cement plants, from incinerators, and so forth, all using this magic class of materials that are due to Professor Yagi. So I'd like you to join me on this extraordinary mission, and thank you very, very much for your attention.